different type of failure criteria or criterion. We said usually if you are talking about a yield point and we're talking about a uniaxial test, then in this case, so assuming that this is the strain and this is the stress, and this is a uniaxial test probably for steel, this is going to look like this. And then at some point here, we're going to say that this is sigma y, this is the yield point, and before that, you have an elastic region. So this is elastic, and then after that, you have an inelastic region. I mean, in the most general case, we say inelastic just because in brittle material, we don't have an inelastic, we don't have a plastic region. So we have just immediately failure pretty much immediately after the elastic range. So we said that this is the point of inelasticity in the most general case. And this is how we distinguish between the two regions. And we said this is the failure point for us as civil engineers or structural engineers. This is the point which define failure. And beyond this point, we would consider our structure has failed. Now, we realize that this is only possible if we have stress active in one direction. So in the uniaxial test, it's assuming that you are trying to apply the tension on a steel bar, then you have stresses happening in one dimension. And if you look into the stress tensor is going to look like this. Now this is quite comparable I'm using the first failure criteria. This is quite comparable, so you can compare sigma should be smaller than sigma y, and this is called the Rankine criteria, and you can validate this criteria by just comparing the single stress you have in there to the sigma y. But we said also that you have more complex situation where these numbers here are different from 0. So in this case, we need to resort back to the principal stresses. So we have sigma 1, 0, 0. Sorry, sigma 2, 0, 0, and then we have sigma 3. And then in this case, we have other failure criteria. So we have the Tresca one, so sigma 1 minus sigma 1 minus sigma 3 should be smaller than sigma y. Or if we have if you want, you can use the von Mises one. So the von Mises is sigma 1 minus sigma 2 squared added to sigma 2 minus sigma 3 squared added to sigma 3 minus sigma 1 squared, and take this entire thing under the square root. So this should be smaller than the square root of 2 sigma y. And we also mentioned there is the Mohr-Coulumb criteria or criterion, and we said the Mohr-Coulumb would be more relevant to the soils. And you have studied some, I mean, you have seen the Mohr-Coulumb previously in geotechnics, I assume, or foundation engineering. So for the Mohr-Coulumb, we had the maximum stress should be smaller than the normal stress on the same plane where you have the maximum stress multiplied with internal friction angle added to some constant we call the cohesion. So whenever this is satisfied, then the material is basically in equilibrium, or the material is stable. This has not failed yet. When we look into the material behavior in one dimension, is relatively obvious to compare to sigma y. But once we move into the 2D case, then the behaviors start to get more complicated. So in this case, we have a yield point, but when you look into these sort of equations, you don't have a yield point anymore. In fact, you have a yield surface in the most general case. So I'm going to discuss this yield point, just going to expand on the concept of the yield point, as we move from 1 dimension to 2 dimension or 3 dimension. Let us start from something simple, if possible. Let us start from the 2-dimensional case. So I'm going to have the stress tensor to be sigma 1, 0, 0, 0, sigma 2, and 0, 0, 0, and 0. We are discussing a 2-dimensional case, so we're just moving from this case, this is 1-dimensional, to the 2-dimensional case, which is here. All right, so a 3-dimensional case, we ignore the stress or we neglect the stress in the 3rd dimension. The 3rd dimension, the stress would be 0, so this is all zeros. We have 2 stresses there. Now I want to have a description for the failure point, and I won't be able to do this on a 1-dimensional curve, just like I did before by drawing the strain-stress relation, but I will be able to do this on a curve where I draw the relation between the sigma 1 and sigma 2 and the failure point. So I'm going to draw this on a curve that relates sigma 1 and sigma 2. And let us start from the Tresca criteria. So this is sigma 1 minus sigma 3 should be smaller than sigma y. All right, in this case, we have sigma 3 to be 0. So I'm just going to, I'll probably just highlight it. I'm going to need the equation later. So we know that sigma 3 is equal to 0. And then I'm going to have sigma 1 should be larger than sigma y. So if you look into this axis here, you have a point where sigma 1 is equal to sigma y. So at this point, exactly, you can identify the failure. All right, so at this point, you have the yield. Beyond this point, you will have yield. Before this point, you don't have a yield. So I'm going to draw an axis here. And sorry for the quality of my drawing again. And then I'm going to cross out everything outside this point here. All right. So beyond this point, we have failure. Before that, we don't have any failure. Now let us forget about the axis of sigma y and move along the axis of sigma 2. Now, in order to be able to move along the axis of sigma 2, sigma 1 should be equal to 0. I mean, at this point here, you have both of them equal to 0. You are moving along this axis. Sigma 1 would stay 0 and sigma 2 would grow. So if you come to this equation, or if you come to this stress tensor, if sigma 2 is larger than 0 and sigma 1 is equal to 0, then we are going to take the maximum principal stress and subtract the minimum principal stress. So sigma 1 minus sigma 3 would not be valid anymore. We have to use sigma 2 minus sigma 3 now. It should be smaller than sigma y. All right? Because sigma 2 is growing, is a positive number, whereas sigma 1 is 0. So we're still moving along this axis here. So you will keep moving along this axis. You will get to the point where sigma 2 is equal to sigma y. And beyond this point, you will again have yield. So I'm going to cross out everything that is happening beyond sigma 2 equal to sigma y. All right? Now, what about this region in there? So how about the behavior in this region in there? Let us pick a random point, probably this point here, and take sigma y equal to 0.7 sigma y. So probably just zoom on this. I think these are different color and zoom on that a little bit. All right. So let us pick a random point, for example, 0.7 sigma y, this point over there, and probably pick another point here. We have 0.5 probably sigma y. And then we compare the stresses at this point here. So at this point, we have sigma 1 to be larger than sigma 2. And then we compare 0.7 sigma y to sigma y, and this is smaller, so this point has not yielded yet. You can keep moving this point closer to sigma y on the sigma 1 axis or the sigma 2 axis. You can get immediately to this point here, which is going to be probably 0.9999 sigma y from the sigma 1 direction, also from the sigma 2 direction, you get to this number. You get eventually to pick which one is larger, and as long as this is larger than sigma, smaller than sigma y, this is still within the elasticity range. Once it crosses sigma y on either this direction or this direction, you get into the case where you has yielded. So the stress has exceeded the yield point. All right. So within this quarter, where you have sigma 1 and sigma 2 both positive, you have this square there. Yeah. Sorry again for the quality of the drawing. So you have this square. This is elasticity, or this is an elasticity region. And beyond this square, everything beyond these points is going to be an inelastic region or plastic region. I'm going to discuss what happens in this quarter here. So if you understand the first bit, it may become easier to understand what would happen in there. All right, so what happens in this quarter? So if you look into this quarter, the stress tensor is going to look like this. Sigma 1 is positive. Sigma 2 here, you are going below 0. So sigma 2 is going to be negative, and you still have sigma 3 to be equal to 0. Now, because sigma 2 is negative, sigma 2 is going to be smaller than sigma 3. So sigma 3 is not going to be what you are going to compare to against the yield criteria if you're looking into Tresca. So you subtract sigma 1 minus sigma 2 instead of sigma 3 as you did in the past. So this should be smaller than sigma 1. All right? Sigma 2 is negative, and negative is smaller than 0. And when you compare the maximum shear, and the maximum shear would happen between the maximum positive number and the maximum negative number. All right? So this is where you change the comparison now. So if you look into this axis, I'm going just to follow the same thing. And let us assume, just for the sake of argument, that sigma y in tension is equal to the sigma y in compression. So the yield point, if you go back to the yield curve, this is positive because this is tension, but assume that you have compression. So this is going to move in the other direction, and then it's going to yield again in the other direction, and it's going to fail eventually. So this is the yield point, and this is the yield point in compression. This is the yield point in tension. And just for the sake of argument, let us assume that the sigma y in tension is equal to sigma y in compression, that the material is going to behave in this way. This is just an assumption. In the general case, it wouldn't. Just for the sake of argument and for the sake of this example, let us assume that it is the case. So now look into this quarter here. Again, we are comparing against sigma y. If sigma 1 exceeded sigma y along this axis here, at this axis, again, sigma 2 is equal to 0, and sigma 3 is equal to 0. If we exceed this point, if sigma 1 goes beyond sigma y, then this would lead into the yield. And then beyond this point, again, everything after this point is certainly yielded. Now let us move along this axis here. Along this axis, sigma 1 is equal to 0, and sigma 2 is a negative number. So we go to this equation here. So if you look into this equation, you'll see that sigma 1 is now 0, and you have sigma 2. So sigma 2 is taken as an absolute number. So you forget about the negative sign if you want, and you compare sigma 2 to sigma y, because, I mean, in compression and tension, both are the same. So you can move along this axis here, and you get to the point where you have sigma 2 equal to minus sigma y. Once it gets to minus sigma y, this is 0. So beyond this point, again, you have failure. So beyond this axis here, you have failure. Now let us compare the same thing. I'll just do the same comparison which we did before for sigma 1 and sigma 2 being something other than 0. So basically what would happen in this quarter. So I think this is probably the tricky bit. So please pay attention. Let us take a point here and a point here. So let us assume that this is 0.25 sigma y, and this is minus 0.25 sigma y. All right. So at this point, you have sigma 1 minus sigma 2. So at this point here, you have sigma y 0.25 sigma y. This is sigma 1 minus 0.25 sigma y. And then you have 0.25 added to 0.25, and this is 0.5 sigma y. See, because minus is plus, so you have 0.5 sigma y. So basically, you are adding these two numbers together. So basically, whenever the addition of this number is going to go beyond sigma y, then in this case, you will have failure. So in this case, if you go to this point, 0.7, so I'm just going to use exactly the same point, 0.7, and then on the other side, you have 0.5. So you have 0.5 added to 0.7. And if you compare numbers now, if you compare 0.7 added to, I probably just write minus 0.5. This is sigma y and sigma y. So this is 1.2 sigma y, and this is certainly larger than sigma y. So if you take this point, then you will see that this is a yield point. So what is the border between not yielded and yielded? The border would happen along this line here, and this line would cross the point where you have 0.5 and 0.5. It is so bad. My drawing is just horrible today. So if you have 0.5 and 0.5, so it's basically 0.5 added to 0.5. I'm just going to remove these points. Just to clean everything. This is the axis there. And this is 0.5. And this is 0.5 sigma y. And then along this line here, so this minus sigma y to plus sigma y crossing the point of 0.5 and 0.5, everything beyond this will have yielded. Everything within is still going to be within the elasticity range. Now, if you do the same thing for the remaining 2 quarters, this is what you get. So if you look into this picture, this is basically the sigma, oh my God. And this is sigma 1. So this is sigma 2 and this is sigma 1. So this is the first quarter. This is the second, or this is the fourth quarter. This is the second quarter, and this is the third quarter. So you'll see that this is basically what the yield surface would look like. Now, before we had, as I said, before we had a yield point, so you can see here we had a yield point, just one point. Now we have moved into a yield surface. So this is an entire, in 2 dimensions, this is a curve, but you can imagine that this is in 3 dimensions going to look like, it's going to look like a surface. All right. Now you can do the same thing for the von Mises. I probably just write von Mises there as well. So the von Mises criteria is sigma 1 minus sigma 2 squared added to sigma 2 minus sigma 3 squared added to sigma 3 minus sigma 1 squared should be smaller than 2 sigma y squared. I'm just going to keep the squares for the time being because it's easier to draw the curve. So in this case, you will struggle to draw a square root function. So it's easier to do it this way. So in this case, I can cancel sigma 0. So sigma 3 will be equal to 0. So I'm just take it out. So this is 0 and this is 0. I'm left with sigma 1 squared minus 2 sigma 1 sigma 2 plus sigma 2 squared. And then I have sigma 2 squared also from the second curve, also from the second bracket, and from the third bracket, I have sigma 1 squared. And this should be smaller than 2 sigma y squared. And this is sigma 1 squared, sigma 1 squared, sigma 2 squared added to sigma 2 squared. So basically, this is 2 sigma 1 squared added to 2 sigma 2 squared added to, or subtracted from 2 sigma 1 sigma 2 should be smaller than sigma y squared, 2 sigma y squared. Now, if you try to draw this, you get this curve in there. So just to compare it to the previous case, so this is, oops. This is the first quarter, and this is the fourth quarter. So it looks like this. I've got the picture here. So you can see Tresca compared to von Mises. So this is the dashed line is the Tresca one, and the continuous line is the von Mises one. So you see that the von Mises is slightly less conservative than Tresca. Tresca would consider the yield to be happening within a smaller region, whereas the von Mises would consider the yield to happening within a larger region. So I said it is more conservative because at this point, for example, here, if you pick this random point, this point would still be within the elastic range according to von Mises, whereas for Tresca, this point is from the yield region. So this is a plastic region according to Tresca, but it is still an elastic region for the von Mises. So as a designer, as I said, it is completely up to you to decide on what criteria you use, and it's going to lead into basically your design being slightly more conservative, and probably this criteria will be more suitable for a specific type of material or not suitable for another type of material. To consider a two-dimensional case, so a two-dimensional case, I mean sigma 1, 0, 0, 0, sigma 2, 0, 0, 0, and 0. So this is the stress tensor we have. But of course, we can get a situation where sigma 3 also is different than 0. And if we have the full stress tensor, we don't have a curve like this. We have a three-dimensional surface. If you are interested, you can read about this in either the books I've suggested to you, or you can find it on the internet. I mean, this is von Mises criteria on Wikipedia page. Or this is the Wikipedia page for the von Mises. Now, this picture here is basically the yield surface for von Mises. So you can see the Tresca yield surface there. On top of it, you have the von Mises. If you have the cross section in 2 dimensions, so the green circle is the cross section in 2 dimensions. So you have the cut happening along this circle here, and this is the plot. But if you look into the entire thing in 3 dimensions, so you have sigma 1, sigma 2, and sigma 3, so you have this happening along the 3 axes, then in this case, this is going to be the green cylinder. So the green cylinder is the yield surface for von Mises, and the prism inside is the Tresca one. So the surface that presents a prism inside the cylinder is going to be the Tresca, and then on the outer side you have the von Mises, and then again you get to a situation where this is not going to be realistic. So if you go along the axis of the cylinder and you go away up to infinity, you can go as far as to sigma 1 and sigma 2 and sigma 3 equal to infinity, where the material will never yield according to von Mises and the Tresca. So this is where you visually see the problem with the Tresca and von Mises. So you can imagine at the axis of the cylinder, no matter how far the cylinder would go, the axis would still always be within the elastic region. I think it's an interesting read for you to go through. So you just have a look into this. I think there's more information on the behavior in 3 dimensions, and also you can look into other other failure criteria. And so, for example, we discussed Mohr-Coulumb, we discussed the Tresca, but we did not discuss, for example, Hooke-Brown failure criteria. You can look into many other, I mean, there's quite a few other failure criteria, but we did not discuss all of them, and just enough to discuss the ones that are most relevant to civil and structural engineering.